So let's look at one of the more important strength of material equations in general, but for this class, a very important one. And that is the idea of we're looking at that linear elastic region. Now, as we look at that linear elastic region, if it's linear, that means there must be a linear equation that relates the stress to the strain. And as we look at all of our curves, we've seen that there's definitely, you increase stress, there's a proportional increase in strain. So this was first discovered by Robert Hooke in 1676. And he did this by using springs. Now, this is known as Hooke's Law. And so if we look at it, what Hooke's Law tells us is that we have our stress, and it's related to our strain. Now, it is related to the strain by what's known as a constant of proportionality, which is basically, in this case, the slope of the line. And so what we're going to do is we're going to call that constant of proportionality E. So no Greek letters here. We go right back to the Phoenician alphabet. And so E is defined as, we call that the modulus of elasticity. You will also see this called Young's modulus, because Young did some work on formalizing this. So either one is the correct thing. So the modulus of elasticity or Young's modulus. Now, this is, here we'll box this, because I know everybody likes the little boxes. This is a critically important equation. Now, Hooke's law only works for materials that exhibit linear elastic behavior. Basically, the materials that we'll be dealing with in class will. Things that don't have linear elastic behavior would be like viscoelastic materials, and those are materials where their strain rate changes depending on how much force you apply to it, one of which would be your knee. There's a lot of stuff in your knee, the collagen that's holding everything together, that's a viscoelastic material. The more force you put on it, the less strain. But that's an aside. The other important thing is not only does this only work for materials that exhibit linear elastic behavior, once again, like I said, everything we're going to do in this class, but it only applies within the elastic portion of the material. So if we go back to our stress strain graph, and it does one of these, there's the yield stress, there's the proportional limit. So it's within this zone where this applies. Now, truthfully, this breaks down here at the proportional limit, because after that we're still in the elastic region and we tail over. But what we typically do is we just assume that it holds all the way to the yield stress. You do have this area right here in between the proportional limit and the yield stress where it's not really holding true, because it is no longer, the equation doesn't hold, but we just assume it does. There's a little bit of error in there, but not too much. So let's look at it. What are the units of E? Because as we've said, units are really important. So let's look at our equation and find out what they need to be. So the units of stress are going to be in force per area. So force per length squared. And if we look at strain, well, technically, as we've talked about, strain's technically unitless. It's length over length. So for the modulus of elasticity, that tells us that the units have to be in force per length squared, because it's the only way the equation would balance out. So force per length squared, so what am I talking about? I'm talking about newtons per meter squared, which is our pascals. And these are going to be very, very big numbers. So we're typically not going to be seeing pascals. We're not even going to be seeing kilopascals. We're going to be seeing megapascals. We're going to be seeing a lot of gigapascals. Remember, this is times 10 to the 6 times 10 to the 9. In the English system, we're going to end up seeing pounds per square inch. What you'll see a lot then is KSI. Remember, KSI is 1,000 PSI. Now, let's take a look at this chart right here. So these are all the same steels and irons, but we've made some changes to them, changes to the chemical compositions. Pure iron, carbon steel, high strength, low alloy steel, quench tempered alloyed steel. So these are all been heat treated differently, and so they have different, if you can see it, they have different curves here once we get out into the plastic deformation. But you'll also see they all have the exact same Young's modulus. And as the slide here says, it's affected by alloying, heat treating, manufacturing. Stiffness is not. No matter what we do to the material, it's always going to have the same Young's modulus. And as I said, this is of critical importance to strength of materials work, especially in this class. Almost every advanced topic that we're going to do, we're going to be starting with the assumption that we're in the linear elastic region. And then once we make that assumption, we're going to sit there and be able to go, okay, well, since I am in the linear elastic region, I know Hooke's law for normal stress is valid, and I'm going to be able to use that to do other things. Once you get outside of the elastic region, you get in the plastic region, every equation in this class that we're going to do is going to change, because now we have to take into account plasticity, and things change a lot.